We'll begin with unit number 1, that is random variable and random process from this lecture onwards. So to begin with, I'll just give a classification of signals. Signals, as we all know, they can be divided as deterministic or random. So broadly, we can categorize signals into categories, that is deterministic and random. Deterministic signals are, you can say, those signals which can be reproduced exactly with the repeated measurements, or we can say they can be represented by exact mathematical expressions. Represented by exact mathematical expressions. For example, unit step signal. We have an exact mathematical representation for a unit step signal, right? This is a kind of a deterministic signal. So I'm repeating once again, deterministic signals are those which can be reproduced exactly, or they can be represented by exact mathematical expressions. Okay, we are aware of outcome of that signal at any particular instant of the independent variable, or you can say the dependent independent variable on which the signal is dependent, right? Like time. On the other hand, random signals are those signals which cannot be repeated in a predictable manner. It is just opposite to the deterministic signals. It cannot be repeated in a predictable manner, or you can say it cannot be represented by a exact mathematical expression. Cannot be represented by exact mathematical expressions. Okay, for example, noise in any system. Noise in any system is unpredictable, and that is completely random in nature, and hence it's a random signal. Okay, so most of the noise signals that we encounter are random in nature. Okay, and although it is not predict the exact or precise value of the random signal in advance, however, it may be described, but we need some you can say measures to quantify the random signals also, right? So although the precise value cannot be found, but we have some other methods by which we can predict these random signals. These random signals, they can be described in terms of their statistical properties. They can be described in terms of the statistical properties of those signals, such as average power in random signal, their probability density function PDF, their CDF. So these are the statistical properties which can be used to describe these random signals. They cannot be predicted exactly or precisely, but they can be described by the means of these statistical properties. Now let us define what is a random variable. It's a very, very important concept for the communication systems, because the noise we are dealing with is random in nature. Okay, so the very simple way to understand a random variable is that it is a variable whose possible values are the numerical outcomes of a random phenomena or event. I'll just write down the definition first. It is a variable whose possible values are the numerical outcomes of a random phenomena, usually represented by capital X. So it's a variable whose possible values are the numerical outcomes of a random phenomena. What does this mean? Now when we perform any experiment, the possible outcomes are you can say known as events of those events of that experiment, right? The possible outcomes. Right? And further, what we can do is we can find the probability of those events. So this chain of process helps us in analyzing a random variable. We perform an experiment. For example, we throw a coin or we throw a dice. Okay, there are 6 possible outcomes of a dice. These are the possible events. It can have values 1, 2, 3, 4, 5, 6, right? So these are the possible outcomes which will be represented by the random variable. See, it's a variable whose possible values are the numerical outcomes of the random phenomena, and hence we can find out the probability of occurrence of each event. So that will help us, since this whole experiment is random in nature. Every time you throw a dice, the expected outcome, you cannot predict the expected outcome, right? If it is kind of unbiased dice. So this entire chain of process is required to analyze a random process, and that is the maximum information or knowledge that we can have about a random process. And each you can say the possible outcome is known as sample point of that experiment. It is the each possible outcome, and combinedly all the sample points are known as sample space. Combinedly all sample points the sample point is represented by S, and this combined, if we combine all the sample points, it is known as sample space. Like for example of throw of a dice, the sample points is represented by 1, 2, 3. These are the possible outcomes, and the sample space is combination of all these possible outcomes. This is the entire sample space. Now the random variables can be further divided into 2 categories, that is discrete and continuous. Discrete random variables and continuous random variables. The difference between these two is very simple and basic. Discrete random variables are those that can have countable or finite number of distinct values, can take only finite or countable number of distinct values. For example, just like the number of children in a family, these are finite in nature, right? So we can easily number those 1, 0, 1, 2, 3, 4 and so on, right? On the other hand, continuous random variables are those which can take infinite number of distinct values. Can take infinite number of distinct values. Now let us discuss about the statistical properties which help us to analyze the random variables. We'll begin with the CDF, that is cumulative distribution function. It is one of the important statistical property of any random variable, CDF, cumulative distribution function. and as the name suggests, it is represented by capital F subscript x, which is the random variable. Alright, this is the symbolic representation of a CDF, and as the name suggests, it is cumulative distribution. It cumulatively you can say accumulates the random variables. That is, fx of x is nothing but equal to probability that x is less than equal to x, where capital X represents the random variable and small x is the running variable. Okay, so for the random variable x, probability of the event that x is less than x is the cumulative distribution function. So this is how we can define the CDF of a random variable. So this is one way of analyzing or representing a random variable, that is CDF. Now let us look at the properties of the CDF. First property is that it is bounded between 1 and 0. Since it is a probability, this CDF is nothing but probability of this event. Now since it is probability, so it has to be bounded between 0 and 1. It is bounded between 0 and 1 since it is a probability function. And the second property is the CDF of any random variable is a non-decreasing function. CDF is always a non-decreasing function. That means fx x1 if x2 is greater than x1. Okay, this will be the relationship if this is the condition. That is, it is always an increasing function, it is never a decreasing function, right? Third property of CDF, and the very important property, is that fx at minus infinity or the initial value is 0, always 0. Fx infinity, the final value is 1. So these are the three important properties of CDF that will be used frequently. Now let us take up an example to understand the CDF, right? We take the simple example of throw of a dice. Okay, we already know there are 6 possible events. So the random variable x, this is the random variable x represents the throw of a dice. So the x can have values 1, 2, 3, 4, 5 and 6. These are the 6 possible values that the random variable x, which represent the event that is throw of a dice, can have. Okay. So now we know that the probability of occurrence of each event, if this dice is of unbiased dice, is equal, and that is equal to 1 by 6, right? So if we try to plot the CDF of this event or this random variable, we plot the CDF of this random variable which represent the event that is throw of a dice. This 0, 1, 2, 3, 4, 5, 6, 7, 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, 6 by 6. Okay. So if we analyze what is CDF at 0.5, it will be nothing but probability x less than equal to 0.5, right? So what will be this probability? It will be 0. What will be fx of 1? It will be probability x less than equal to 1. What is this probability? X less than equal to 1. It is nothing but equal to 1 by 6. So till 0 to 1, the probability or the CDF will be 0. At 1, the CDF will be 1 by 6, right? Similarly, what will be the fx 1.5? It will be probability x less than equal to 1.5, which is nothing again but equal to 1 by 6. And if you look at the CDF at 2, it is probability x less than equal to 2, that is equal to 1 by 6 plus 1 by 6, that is 2 by 6. Simple probability concepts, nothing else. So from 1 to 2 the probability remains 1 by 6, and at 2 it becomes 2 by 6, and same with the other points. So it's a staircase kind of a scenario, and you can easily see initial value is 0, final value is 1, 6 by 6 is 1. It is a non-decreasing function and it is bounded between 0 to 1. We can see all the properties from here of the CDF. This is how we can plot the CDF of any random event. Okay, next we'll have a look at the another important statistical property of random variable, that is probability density function, PDF. Probability density function, and commonly used as PDF. The standard notation of this PDF is small f subscript x, which is the random variable, and the running variable small x. This is the standard notation of the PDF function. You can say it is an alternative description of probability distribution of a random variable, and it is often very useful. Okay, how do we define it? The PDF of any random variable x is nothing but it is the derivative of the CDF. PDF is nothing but the derivative of CDF. Very important expression. And if you look at the vice versa, the CDF is nothing but integral of the PDF. Very important two expressions, relationship between the PDF and the CDF, and this is how we define a PDF. It is nothing but derivative of the cumulative density function. Now, as I already told you that it is an alternative description of the probability distribution. Probability distribution. It is not a probability, but it is a representation of probability. Why do we use the term density in here? The PDF stands for probability density function. Okay, the term density function arises because it gives the occurrence of the density in the range of the interval. It gives the occurrence density in the range of the interval. This is the important application of PDF, that it gives you the occurrence density of the event in a particular range of the interval. For example, x, if we talk about the interval x ranging from x1 to x2, so the probability x1, this can be simplified as probability x is less than equal to x2 minus probability x is less than x1, right? And this is nothing but CDF at x2 minus CDF at x1, and that is nothing but the integral of the PDF over the range x1 to x2, right? So we can clearly see that this PDF, if you take the integral of the PDF in a particular range, it gives you the probability of occurrence. This is the reason it is used to find out the occurrence density in a range of interval. Okay, we'll look at some other examples also based on this concept, that will give you a better picture of this the concept. Now let us look at the properties of PDF. First one is it is a non-negative. PDF is always greater than 0. It is non-negative in nature and for all values of x, and that is quite intuitive since the CDF is a non-decreasing function. So since CDF is a non-decreasing function, its derivative will always be a positive quantity. So the PDF is always a non-negative quantity. That is the first property. Second one is area under the PDF curve is unity. If we integrate the PDF over the range minus infinity to infinity, or we can say the area under the PDF curve is always unity. Very, very, very important expression. And the proof of this is also very simple. If you look at this integral, it is nothing but equal to f of infinity minus f of minus infinity, and that is equal to 1 minus 0, that is equal to 1. And third property we have already discussed, that is the CDF can be derived by taking the integral of the PDF. Let's do an example based on the concepts studied till now. The question is a random variable x. The x is the random variable, and it has the PDF a exponential argument b modulus of x. This is the PDF of the random variable x for all values of x ranging from minus infinity to plus infinity, and the value of a is 3, and the question is find, first part, a relation between a and b. Second part is we have to find out the CDF of this random variable, and third part is probability that the random variable x lies between -1 and +2. Okay, so these are the three things that we have to find, and we are given with the the PDF of the random variable only. Okay, so let us begin. We know that the PDF given to us is a e raised to power minus b modulus of x. Let us expand it, simplify it a bit. A e raised to power bx for the values of x minus infinity to 0, and a e raised to power minus bx for the values 0 to infinity. Okay, this is how we can alternatively represent this PDF, just expanding simplifying the modulus part. Now the first part is to find out the relationship between a and b. We know the property that the PDF, integral of the PDF is unity, or the area under the PDF is unity. That is, this is equal to 1. Let us use this property. Substitute the value of the PDF for different ranges, that is minus infinity to 0 and 0 to infinity, and equate it to equal to 1. So it becomes equal to 1. If we simplify this integral expression, we get a by b e raised to power bx for the range minus infinity to 0 plus range from 0 to infinity, and it's equal to 1. If you simplify it, it is a by b 1 minus 0 plus a by minus of b 0 minus 1 is equal to 1. So this is equivalent to a by b equal to 1, and b is equal to 2a is the relationship between a and b, and since a value of a is given as 3, so b is equal to 6. So this is the answer of the first part. Second part is to find out the CDF. CDF, as we know, it is nothing but integral of the PDF, and we are already given with the PDF. So since the PDF has a modulus operator, so we'll divide this range in negative and the positive part. So case 1, that is for x less than 0, the PDF f of the CDF is equal to minus infinity to x a e raised to power bx dx, right? Because for this for x less than 0, this range, this is the given PDF, right? If we simplify the modulus operator, and if we simplify this integral, it comes out to be 1 by 2 e raised to power bx, and this is for x less than 0. This is the CDF for x less than 0. Case 2, for x greater than 0, the CDF will be equal to minus infinity to 0. It will have both the values, plus 0 to x a e raised to power minus bx dx. And this part we already know. If you substitute x is equal to 0, it comes out to 1 by 2 as seen in the part 1, plus if you simplify this integral, it comes out to be 1 by 2 minus of 1 by 2 into e raised to power minus bx minus 1, and if you simplify it further, it becomes 1 minus 1 by 2 e raised to power minus bx. So for this, for the range x greater than 0, this is the CDF. The combined CDF can be written as 1 by 2 e raised to power bx and 1 minus 1 by 2 e raised to power minus bx for x less than 0 and for x greater than 0. This is the combined CDF. Moving on to the third part, where we need to find out the probability that the random variable x lies in the range minus 1 to 2. This we can easily find out with the help of the PDF. We can just integrate it in the range minus 1 to 2. We can integrate the PDF in the range minus 1 to 2 to find out the probability of occurrence of x in this range. As simple as that. And this is the important application of the PDF, that it can find out the occurrence probability in a given range. So let us simplify this integral. So from minus 1 to 0, the PDF is a e raised to power bx dx plus, and for the range 0 to 2, it is a e raised to power minus bx dx. And if we simplify if we simplify these two integrals, we get 1 minus 1 by 2 e raised to power minus 6 plus 1 plus e raised to power minus 6. This is the final answer of this occurrence of random variable x in this range. So this was all about the two important statistical properties of any random variable, that is PDF and the CDF. We'll discuss about the other statistical averages like mean, variance of the random variable, moments of the random variable in the next lecture. Thank you.